First subtopic in chapter 2 is on the basic fundamental of semiconductor. Okay, basic fundamental of semiconductor. Okay, you guys biasa dengar tak what is the semiconductor? What is that? What is the semiconductor? It is there are the types lah, few types. For the semiconductor, there are the actually this come from conductor, semiconductor and the insulator. Okay. For the conductor, this one is highly conducting material. By default ataupun by nature, from the original compound ataupun original material dia tu memang it can conduct electricity. Okay, contohnya apa? What are the contoh yang conductor? Apa? Metal. Dekat dalam wire tu metal lah kan? What else? Lagi? Silver, copper. Kan? Okay, so that one is by default memang dia conductivity very high. So memang sebab tu orang kata kalau you kena elektrik jangan pergi pegang besi-besi. Okay, pegang insulator. Those solid material whose conductivity is very low ataupun virtually zero by default. Okay. Okay, and then for insulator offer infinite resistance to current flow. Sebab tu when you get electricity punya shock, peganglah rubber, kayu. Okay, kerusi meja yang plastik ini. Okay, that one is contoh-contoh for the insulator. Whereas for the semiconductor, it is the compound yang kita boleh modify. Okay, the compound that we can modify. For the conductors ni, dia macam yang copper, ion, metal, that one kadang-kadang mahal and then sources nak dapat tu susah. Sebab tu kita tak guna 100% on this conductor and conductivity dia very high, boleh bahaya juga. Okay, sebab tu kita guna on the semiconductor. Semiconductor can be neither good conductor or insulator, depends on the material. Okay, conduct little electricity. Okay, for the conductor, it can be copper, widely used in electrical wiring and components. Also we have the aluminium and silver, but then for the silver dia mahal kan, copper pun mahal juga. Okay, for the semiconductor, semiconductor is the compound yang kita dah modify. Okay, it can be silicon, germanium or gallium arsenide. Most of the as you guys can see dekat sini, this one silicon, germanium, gallium arsenide. Okay, this one kenapa? Because it has the properties untuk jadi good semiconductor. Okay, and then for the insulator, conduct little electricity ataupun cannot conduct electricity. It can be rubber, glass, wood, plastik. Okay, benda-benda yang tak mengalirkan elektrik. Okay, manusia bahaya juga kan kadang-kadang kan. Jangan pegang orang lah, kecuali kalau dia pakai baju yang tebal ke. Manusia tu boleh jadi konduktor kot. Nanti kita try. Dia kena duduk dekat tengah padang, biar kena kilat dulu. Okay, alright, so what is semiconductor? We want to focus on the semiconductor because this one yang kita because we want to modify on the compound dekat dalam material dia tu. Okay, has conductivity rate in between metals and insulator, we call it a semiconductor. Okay, and then behave as an insulator. It can be insulator at zero temperature and show some connectivity. Example, we have silicon, this one is Si, germanium, Ge, and gallium arsenide, GaAs. Okay, and as compared between these three, silicon, germanium and gallium arsenide, silicon is the most commonly used as compared to germanium. Why?
Easily accessible, cheap.
most abundant element in earth kan. Actually it comes from, pernah dengar pasir silika ataupun batu kan, batu silika. So that one is the original, dia punya ni lah yang belum diproses. Okay. And one more thing is the germanium is slightly expensive to produce. Okay. And silicon is also more stable to fabricate, has better properties, has higher melting point, wider band gap and higher electron mobility. Also this one is more compatible as compared to germanium. Okay, silicon and germanium. Okay, most commonly used semiconductor material is silicon. Okay, we have the elemental semiconductor composed of single species of atom, and also we have the compound semiconductor. This one you belajar dekat dalam chemical kan. Okay, yang ada bulat-bulat, ada elektron, ada atom tu, that one. Okay. Compound semiconductor are widely used in high speed devices. Pernah dengar tak high speed devices? Ataupun kabel-kabel yang charger punya kabel tu kan, fast charging. Okay, and also in optoelectronic devices such as LED, laser diode, photo detector and also in the photodiodes. That one dalam sensors yang you guys guna for electronic project. Okay, and for high speed devices such as kalau dalam lab we use dekat dalam oscilloscope kan dia ada punya screen juga. Okay, and in fiber optic for communications, also dekat dalam transistor, CPU, in microprocessor, also dekat dalam high speed memory devices such as DDR, ROM ataupun SSD, kad yang kecil tu. Okay, and kat mana lagi? Dalam solar cells, also dekat dalam IC, dalam integrated circuit yang kecil warna hitam tu, ada banyak kaki tu. Okay, dekat dalam tu. Alright, and also kalau dekat dalam in medical area, we apply dalam medical imaging devices yang buat MRI. Okay, in automotive electronic, we apply dalam engine control unit. We use when we use modern vehicles for engine control, yang electronic punya control. Okay, so that is for the applications lah. Okay, kat sini ada tulis use in high speed devices and optoelectronic devices. Tadi yang saya mention tu contoh-contoh optoelectronic devices. Alright, so this is the atomic structure. This one is A is for silicon, B is for germanium, this is for gallium arsenide. So gallium arsenide, the combinations between two compound lah. Okay, and all these compounds, all these silicon, germanium and gallium arsenide has 4 valence electron at the outer cell. Kalau you bilang, dia akan ada 4, 1, 2, 3, 4 sama. Okay, semua ada. Yang ni ada 1, 2, 3. Yang ni ada 3. Yang ni je, silicon and germanium. Okay. Alright, so now we want to relate with the conductivity, dan kita kena pergi to conductions and valence band. Okay, conduction and valence band. Kalau conduction, we call it as the EC. Kalau valence band, EV. Okay, and then the mana gambar dia? Okay, this one. The forbidden gap or the gap between both EC and EV is the energy gap, EG. This one Okay, this is conduction. Yang atas, at the bottom is the valence band. Okay, and this one is the EG. Okay, let's say if we have this one is in the conductions and valence band, dia akan ada electron kan. So the electron will jump from bottom to the top. Bila dia jump, dia akan tinggalkan hole. Daripada elektron dekat bawah, dia akan jump, dia akan tinggalkan hole kat bawah. Okay, let's say this one partially filled band, ataupun this one we can say this is for semiconductor, ataupun this one yang overlap band ni, this is very good conductor sebab dia overlap. So the electron can easily move to the conduction band. Bila makin jauh the gap, makin susah elektron nak jump. So the conductivity akan jadi very low, approximate to 0 kalau makin jauh. Kalau makin dekat ataupun dia bertindih, that one is conductivity very high. Okay, so if this one overlap, meaning that conductivity dia very high lah. This one might be for metal, copper. Okay, this one pun sama on the energy level. Okay, this one is energy level when we compare dekat dalam this electrons nucleus ni. Tapi yang tu kita potong macam ni. So dia ada this one yang menghampiri nucleus yang tengah dia tu, and this one is the outer band tu. Okay, so dia ambil step 1, dia potong macam potong kek, kan? So meaning that between each of the layer tu dia ada energy gap dia. Okay, whereas for this one tadi ni, ini kita hanya ambil satu layer je. Okay. Okay, this one sharing that electron move from valence band go to conduction band. Okay, you guys boleh baca nanti dia punya penceritaan. Okay, for the insulator, insulator ni yang mana? Yang can conduct electricity ke tak? Okay, that is why has large forbidden gap. Okay, yang value ni dia tak fix lah, normally more than this value. Okay, tetapi it also, kalau for semiconductor, dia also effect on the temperature. Sebab it is movements of the ions kan. Kalau temperature tinggi, dia akan lebih aktif, dia akan lebih movements dia nak jump tu lagi aktif lah, bergerak. Okay, yang bawah ni, energy gap of a semiconductor material decreases with increase in temperature. Maksudnya temperature naik, energy gap dia makin rapat. Ni EV, ni EC. Okay, tak nak bagi dia conductivity tinggi, masukkan dalam peti ais. Alright, so this is for the semiconductor. Okay, the explanation dia lah, insulator, semiconductor and the conductor. Okay, for the ni macam komik dah, dia nak cerita from the electrons, it cannot, for the insulator because of the energy gap very large, jauh sangat, dia cannot jump. Okay, for this one still can jump for semiconductor. Okay, for conductor it is partially overlap, consider as overlap. So the electrons can easily move to the conduction band. Alright, this is the three: insulator, semiconductor and conductor. Okay, so now we go for intrinsic and extrinsic. Kat sini pun kalau you guys baca, dia ada tulis conductor, the valence band and conduction band actually overlap. Okay, for insulator, higher energy level, so they cannot move, they cannot jump sebab jauh sangat. Okay, for semiconductor, dia ada gap tetapi still can jump, depends on the material dia juga. Okay, so now we go for intrinsic and extrinsic. What is this? Intrinsic, pure material. Semiconductor has a very low level of impurities. Yang original lah biasanya, dia tak ada benda asing. Okay, there is no impurities. Okay, and pure SE and GE, poor conductor, sebab kita tak ada masukkan elemen lain lagi. Okay, for extrinsic, for semiconductor, we has inject some material in the pure material tadi tu. So intrinsic, bila kita tambah dopan, dia akan jadi extrinsic. Okay, tambah dopan. Dopan is the material, the impurity, benda asing. Okay, bila kita tambah dia akan jadi extrinsic. And process of adding dopan, we call it as the doping process. Okay, doping is the process of adding impurities. Impurities is also, we call it as the dopan. Benda yang sama je. To intrinsic, either Si or Ge, to improve the conductivity. Why? Because we want to improve the conductivity. We want to make the energy gap in between valence dengan conductions lagi hampir, lagi dekat. Tetapi it is slightly impossible untuk jadi overlap. Dapat lagi hampir pun is okay dah. As long as the electrons can jump easily from valence to conduction. Okay. Intrinsic ni apa? The original one. Okay. And then how to create extrinsic from intrinsic? Add dopan. Melalui doping process. Dopan is also the impurities lah. Apa yang kita tambah. Tapi what are the impurities yang kita kena tambah? The benda asing that we can add tu kena tengok dah dia punya material. Kan tambah-tambahkan dia jadi makin insulator pula. Instead of we want the gap makin hampir, tiba-tiba jadi gap dia makin jauh. Okay. Tu yang pentingnya R&D. Tak boleh simply buat je. Okay. Alright. So this is for intrinsic. Okay, semiconductor we can classify into intrinsic and extrinsic. Intrinsic, no foreign element. Yang original lah. Yang tak ada tambah apa-apa. Okay. For ni intrinsic. Okay, the extrinsic. For extrinsic, kita tengok ni dulu. N, P and I. This one we call it as the number of electrons and number of protons ataupun holes. Okay. Number of free electrons in conduction band is equal to number of holes in valence band at any temperature. And naught is equals to P naught at conduction band. This one is at the valence band. Dia terbalik lah. This one is majority carrier. Let's say for majority carrier is holes, dia akan sama dengan minority carrier because it is pair kan, electron and holes. Okay, tetapi this one is at the valence band. Okay, so this one is for intrinsic. Intrinsic semiconductor material is the preferred material in electronic industry. To fabricate electronic devices, we can alter the electricity ataupun conductivity by adding amount of foreign element called impurities or dopant. Okay, called dopant. In the process of injecting impurities called doping process. Okay, we inject impurities into intrinsic. The intrinsic plus impurities equals to extrinsic. Okay. Why? Because we want to increase the conductivity of the material lah. Okay. And then the the impurities yang kita add tu, it is very small element pun sebenarnya. Bukannya you nampak seketul apa yang kita tambahan tu. Because now we are dealing with atoms. Electrons kan very small. Kita tak nampak dengan mata kasar. So di sini is the ratio 1 part in 10 million. Kan, so very small amount kan. But then the small amount yang kita inject can alter the conductivity of the intrinsic semiconductor. From the insulator ataupun very low semiconductor, when we inject this very small amount of impurities, dia terus jadi conductivity dia we can increase. Okay. Alright. So what are the impurities yang kita tambah tu? For the impurities yang we inject into the intrinsic to become extrinsic, we can consider ataupun we can classify into P type and N type. Depend on the impurity ataupun dopant yang kita tambah. Okay, dia boleh jadi dua jenis. Sama ada dia jadi N-type ataupun P-type. So kalau contohnya if we want to get N-type, apa yang kita kena tambah? Apa yang kita kena inject? If we want to get P-type, apa yang kita kena inject? Okay. Mainly two types of impurities added into silicon material. Okay, this one is from 5th group in periodic table that you have learned in chemical. Saya pun dah lupa apa compound-compound yang ada in the periodic table tu, but then this is actually from the element kat situ lah. It is not simply kita boleh tambah anything. Sebab tu this one is relate dengan with the chemistry punya periodic table tu. Okay, such as arsenic, phosphorus, kalau group 5. Kalau group 3, boron. Dia ada lagi lah few others. This one on the scientist dia dah kaji dah what are the components ataupun element compound yang boleh contribute to the electricity connections tu. Okay, that is why suggest to add from group 5 ataupun group 3. Okay, either we add electrons in the conduction band or we create holes in the valence band. Okay, we inject electrons dekat band yang atas, ataupun bila we create holes, maksudnya kita kena push supaya elektron dekat bawah dia jump pergi atas. Okay, dia jump pergi naik atas. So bila dia jump naik atas, dia akan leave the hole yang kosong. Okay, of the intrinsic. Sebab daripada kita nak create from intrinsic biar jadi extrinsic kan, so kita kacau intrinsic punya properties dalaman dia tu. Okay, so this one is for N-type material. Dia ada dua jenis lah, N-type and P-type. And please remember that for this diode, actually benda ni kita nak buat diode. For the diode normally kita guna dalam switching purpose. Okay, untuk switching. So for the switching dia ada dua jenis, high and low, on and off. Okay, kalau this one contohnya for N-type, high equals to 1 equals to active, low equals to 0 equals to not active. Okay, high equals to 1 equals to active, maksudnya it is on, this is off. For N-type, by default dia macam ni condition dia. How about P-type? Kalau P-type macam mana? How about P-type? Condition for P-type. For P-type dia terbalik. Kalau dia terbalik maksudnya when we put it high, active, it is off. Dia terbalik. Dia still on, tapi dia off. Condition dia for P-type. Tulis sini, still N-type, N-type lagi. Okay, for P-type, on, low, 0, not active. Oh sorry, dia aktif lah, dia aktif. Mana pula saya punya ni? Dia aktif. Okay, off, high, 1, not active. Dia terbalik lah, terbalik from the P-type. Okay, there is also few conditions di mana kita nak buat switching tu dia terbalik. Contohnya kalau switch kat depan dengan switch kat belakang punya position dia terbalik kan. So dia datang from this concept lah. Itu beza dia P-type and N-type. Okay, by default which one you prefer, P-type ke N-type? Tapi ada juga kadang-kadang orang suka benda yang terbalik kan. So dia konsep dia macam tu lah. There is certain situation where we need to use the P-type. Okay, by default kita pakai N-type, tapi for certain situation kita guna P-type. Okay, so this is for N-type. Kita balik semula. I'm not going to explain on this one. Ni adalah elemen dekat dalam the kalau tengok dekat dalam dia punya ni valence, apa nama yang kat tengah tu adalah nucleus. Dekat setiap satu bulatan dia tu. Okay, this is explanations dia. adding fifth element in one extra hole. So you guys can read this one. Okay, and please remember that all this process will be affected by the temperature. Kalau temperature naik, movements of the electrons akan lebih laju lah, lebih aktif. Okay, due to the kinetic, dia boleh relate with the kinetic energy macam tu. Okay, so this one is okay, bila kita inject the electrons ataupun electron jump from this one, dia ada donor ionization energy dekat bawah EC tu. Okay, due to movements of the electrons lah. Kalau P-type dia ada P-type dia ada acceptor ionization energy above the EV. Okay, due to the presence of acceptor impurity in pure semiconductor, a new energy level is introduced. Because of the new energy level, so gap dia akan jadi makin hampir lah. Kalau kita increase lagi, gap dia akan naik lagi. Okay, and maybe at one point dia boleh overlap. Okay, tapi agak jarang lah sebenarnya dia overlap. As long as dia dah hampir tu pun dah okay, because electrons can jump from valence pergi ke conductions.
Kalau overlap tu maknanya dia bertinggi kan?
Yes. Dekat dalam metal, sebab tu dia metal very high conductivity. Dia tak ada energy gap antara valence dengan conduction, antara donor dengan acceptor. Okay, dia memang bertindih terus. Alright. So next one, kita nak pergi ke PN junction. Okay, tadi kita dah tengok we have how many types? Okay, semiconductor ada 3 types, semiconductor, conductor and insulator. But then for the semiconductor we have how many types? 2. What is that? P and N. Depend on depend on temperature. Depend on the adding impurities kita lah. Either dia jadi N-type ataupun P-type. Okay. Now, from the P-type dengan N-type, when we put it together, dia ada satu P, satu N. Bila kita letak bersebelahan, dia akan jadi PNN. That is why PN junction. So ini adalah P, dia punya majority carrier dia adalah hole kan? P. Okay, for N, majority carrier dia adalah electron. So bila kita letak dua-dua bersebelahan, what happen to the majority and minority carrier dia? Dia akan attract. Okay, so the attractions tu pun akan mewujudkan arus lah, current. Okay, the term junction refer to boundary between two semiconductor region, or we have P and N, PN junction diode or semiconductor diode. Okay, this one is fundamental when use the transistor. Pernah dengar transistor? Okay, pernah dengar BJT? Bipolar junction transistor, BJT. Okay, this one is the most basic of transistor. Dia ada few lah. Dia ada juga FET. FET is field effect transistor. Okay, for BJT bentuk dia macam ni. Dia ada anak panah. Dia ada NPN, NPNP lah. Okay, for BJT. Kalau FET bentuk dia lain sikit. Dia ada anak panah dia juga. Lepas tu BJT and FET dia ada juga MOSFET, Metal Oxide Field Effect Transistor. Okay, dia ada juga MEDFET, MED-FET, Metal Depletion Field Effect Transistor. Okay, dia ada BMOS, Bipolar Metal Oxide Field Effect Transistor. Dia ada few lagi lah. But then for our syllabus today, for our syllabus in chapter 2, we only cover on the BJT. Okay, and all of that come from the transistor. All the transistor come from the PN junction ni. Okay, for the BJT dia ada NPN ataupun PNP, meaning that awal-awal kita dah belajar N, kita dah belajar P. When we put it together, dia jadi PN junction. Kita tambah lagi satu jenis, dia jadi PNP ataupun NPN. It will become the transistor. Okay, nampak tak dia punya perjalanan? Okay, so this one is for the PN junction. Okay, so this is for constructions of the PN junction. Pernah tengok this symbol? Okay, this is positive, this is negative. Okay, we have two types of this symbol, diode. This one is diode. It can either be silicon. Kalau silicon, the value dia is 0.7 volt all the time. Kalau dia mention silicon diode, then dia macam connection macam ni lah, 0.7. Kalau dia mention germanium, it is 0.3. Okay, if germanium 0.3, if silicon 0.7, voltage drop dekat dalam diode dia. Okay, alright, so this is the PN junction. Kita ada P-type, positive carrier dia, positif pula apa ni, proton, majority carrier dia proton. Okay, hole, okay, hole. For the N-type, majority carrier dia adalah electron. Okay, when we put it these two together, dia akan attract. Okay, yang positif kat sini dia akan tarik negative charge from sebelah. Okay, itu yang dia jadi sini ni, the depletion region. We call it this one as the depletion region ni. Okay, the two formations of P and N will form the depletion region ataupun space charge. Okay, ni bukan UFO space UFO tu, ini adalah space charge. Actually this one is very small, dekat dalam transistor. Saya tak bawa lah pula yang 3 kaki tu, kat dalam benda tu sebenarnya sangat kecil. Okay, dia ada banyak bentuk lah juga, tapi yang benda yang kecil-kecil dekat dalam electronic circuit normally. Okay, because kenapa dia introduce this space charge? Because dia different majority carrier kan, concentration gradient dia berbeza. Satu positive majority, one is negative polarity. When we put it adjacent, sebelah-sebelah, dia akan attract. Okay, and we call it as the depletion region ataupun the space charge region. Okay, ini explanation dia when two isolated semiconductor material, namely we have the N-type and P-type, we put it together, the carrier in the junction will start to diffuse to other region due to concentration gradient, perbezaan polarity. Okay, electrons dia move to P and then become minority. Bila dia pergi dekat sebelah, dia jadi minority lah. Okay, and for holes pula diffuse to N-type, dia akan jadi minority. Dia pergi rumah sebelah, dia jadi pendatang asing. Okay, same goes for the electrons, dia akan move lah due to the perbezaan gradient dia. Okay, and then due to the diffusions of carrier, because of the movement, dia bukan satu tau, dia bukan satu movement, dia melibatkan banyak movements. Okay, due to movements, the diffusions of carriers on both sides, dia akan introduce diffusions current. Okay, due to movements, electron. Yang ni nak pergi sini, yang ni nak pergi sini. Due to the movements, dia gerak, lepas tu yang ini pun nak go to the other sides, dia akan introduce diffusions current. The word diffusions because of the diffusions of carrier. So dia ada dua sides lah, dua directions. Okay, dia hanya berlaku when we put P dengan N sebelah-sebelah saja. Okay. And then kita boleh letak the electric supply. This one is majority carrier dia positive. Okay, this one positive. In here dia ada diffusion current. Okay, when we put external field ataupun external electric field, external sources, dia akan kacau movements of the electrons dengan ion yang kat tengah tu. Okay. Terbalik ni sekejap. Oh. Positif, negatif. Okay, so sini will be positive, sini akan jadi negatif. Okay, bila kita letak electric source, external field, depend on the polarity. This one negative, positive kan. So yang negative charge dekat tengah ni, dekat dalam N, dia akan tertarik ke this one. Dia akan lebih tertarik kepada yang ni, because this one dia ada contohnya 7. So yang ni dia punya concentration gradient dia lebih besar, power dia lebih. So all the negative dia akan tarik pergi sini. Same goes untuk this side. Sini kan dia negatif, so positive carrier kat tengah tu dia akan tarik pergi sini, menyebabkan dia punya depletion region ni makin luas, sebab semua nak tarik pergi ke tepi. Okay, itu bila kita letak voltage source external. Okay, it also affect kalau kita letak terbalik. Kalau voltage source dia terbalik, dia akan menyebabkan dia lagi dia punya gap yang tengah depletion region tu makin makin rapat. Yang tengah ni dia boleh jadi tak ada gap. Okay, depends on the polarity of this one. Okay, let's say kalau kat hujung ni adalah negatif, so di sini adalah positif. So positif dia tak nak dengan positif, dia attract, dia repel kan. Dia lagi tolak. Bila dia lagi tolak, all the holes dia akan bergerak lagi ke tengah. All the electrons akan bergerak lagi ke tengah. So depletion region yang ni akan jadi makin sempit ataupun terus jadi tak ada. Okay, so that is the effect from the voltage source. Kalau yang ni kita letak macam ni, macam yang saya lukis awal-awal tadi. Positif sini kan, so dia akan positif at this side. Sini negatif, so dia akan menolak. Yang merah dia akan tertarik dengan voltage source yang luar. Yang biru dia akan tolak with the voltage source yang luar. Dia akan beri kesan kepada depletion region yang tengah ni. Okay, so that one kita panggil as the drift current. This one, drift current always opposite to the diffusion current. Kalau diffusion tadi dia tertarik ke kiri, for drift current dia tertarik ke kanan. Okay, and actually when we compare antara drift dengan diffusion due to movements of the electron sahaja. Drift is when we apply external field. So which one akan lebih besar effect dia? Drift lah kan, sebab kita bagi sources luar. Boleh? Nampak tak? Nanti you guys boleh baca the explanation dia. Okay, dia ada explanation dia kat dalam ni. Please read. This one is thermal equilibrium. in between the resistor with the voltage. Ataupun there is also IV characteristic of the diode. For IV characteristic untuk diode, for ideal diode dia akan sentiasa macam ni, IV. Okay, sebab diode we use as switch kan. So for ideal diode dia macam tu. For silicon, tadi berapa value for silicon? 0.7. Okay, for germanium, so sini is 0.3. Okay, this one is forward bias. Yang sebelah atas tu forward bias, yang sebelah sini adalah reverse bias because negative voltage kan. Okay, the other one, number 4 is the Zener diode. Zener diode kita akan belajar dalam 2D. Okay, Zener diode is kat sini is, it can be, Zener diode can be either silicon ataupun germanium. So it can be 0.7 ataupun 0.3, but then here is 6.3. Zener diode, the purpose is to cater on the reverse bias kat sini. Okay, nanti kita akan belajar on the Zener diode. So this is all the 4 IV characteristic. Ideal diode, okay, silicon and the germanium. This one is for Zener diode. Okay, forward bias and reverse bias. Alright. This is PN junction yang tadi tu lah, P-type and N-type. Sama je dengan tadi kan, kita dah sentuh dah on this. This one is on the current flow. Okay, we have anode and cathode for the diode. On the PN junction ni equals to P and N ni equals to diode lah. Okay, equals to diode. And dia ada P-type dengan N-type. Dia punya simbol dia is like this. Positive, negative. Positive is P side, positive. N side, negative. This one, cathode, anode. Okay, kalau dalam circuit bila ada diode, please consider as dia macam ni lah. Kalau germanium 0.3. Jangan bila nak buat circuit, madam ada diode ni tak boleh buat ni. Dia it is consider macam battery ataupun voltage source. Tapi value dia kena fix. If the question state that silicon, then 0.7. Kalau ada dua diode, silicon, 0.7 plus 0.7. Tapi kena tengok polarity dia because it has anode and cathode polarity. Okay. Apa lagi ada kat sini? Okay. So yang ini biasing scheme ni yang saya conteng bawah ni. Mana dah? This one. Okay. Due to the polarity of the external electric field, dia akan introduce biasing scheme. Forward bias or the reverse bias. Okay, by default forward bias, reverse bias dia terbalik lah. Okay, depend on the polarity of the external voltage source kan. Macam saya lukis tu, across the two terminals of the PN junction, there are mainly two biasing scheme, reverse bias and forward bias. Depend on the polarity of the external electric field. External sources yang kita sambung tu lah. Okay, for the reverse bias, positive terminal connect to the N-type semiconductor. Kalau yang lukis tadi, which one? Positive terminal connect to N-type semiconductor. Which one? Positive terminal connect to N-type semiconductor. Which one? Merah ke biru? Okay, so this one is for reverse bias. Okay, for forward bias, negative terminal connect to negative N type of the semiconductor. So dia terbalik. Okay. Okay, due to the reverse bias, majority carrier electron in N side will attract towards the positive terminal and holes in the P side will attract towards the negative. Tadi saya dah explain kan? Ya tak? Saya dah explain benda ni kan tadi? Kan? Explain dulu, ayat datang kemudian. Korang baca lah nanti. Okay. Inilah tadi yang kita conteng tu. Ni rupanya circuit dia kan? Okay, sama tak? Positive terminal connect to N type semiconductor. Apa macam terbalik ni? Betul lah. Dia punya N dengan P dia terbalik. Tadi kita lukis N dia sebelah kanan. Okay. Positive terminal connect to the N type semiconductor. Ni N type. Negative terminal connect to P type semiconductor. Okay. So dia akan menyebabkan what happen to the depletion region yang tengah tu. Tadi saya dah explain dah pun. Makin luas, makin besar dia punya region tengah. Okay. So this one kita panggil reverse bias. Kita tengok forward bias, tengok circuit dia teruslah. Okay. Ini forward bias, terbalik lah. Kita pusing dia punya polarity. Polarity of the external voltage source. Ataupun pusing locations of the N dengan P kan. So what happened to the depletion region? Dia jadi tak ada. So the electrons can move easily and current can flow easily dekat dalam the diode. Diode ataupun semiconductor. Okay, that is the effect on the external electric field. Okay, we'll introduce drift current. Okay, and then drift current ni normally dia boleh measurable lah. Measurable current. Kalau yang the diffusions tu, because it is very small, dia tak boleh measure pun kat dalam semiconductor tu. Okay, faham tak on this one? Ni apa? PN junction with no external bias. Okay, so this is the symbol dia. Anode and cathode. This one actually material dia. Okay, when there is no VD equals to 0 ataupun the diode is off ataupun polarity dia terbalik, reverse bias lah. When reverse bias, current cannot flow in reverse bias. Okay, because of the polarity external field dia tu terbalik. Kan semiconductor ataupun diode we can use as switch. So bila dia tak boleh pergi, dia tak boleh, dia punya polarity anode dengan cathode dia terbalik, so dia consider off. Switch to off. Bila off, circuit tu tak boleh flow lah. Dia jadi open circuit. Ni open circuit. Alright. So this is untuk diode. For forward bias, this one, polarity and direction of the resulting current ini. So VD is, kalau silicon berapa? Germanium. Okay, so dia auto, you kena tahu. Dia boleh je sambung dengan resistor, pergi dekat voltage source lagi, pergi resistor lagi in the circuit. Okay, but then this one consider kita replace dengan sources ni value. Okay, tengok dia punya polarity. Kalau positif negatif, kalau polarity dia terbalik, sini negatif, then you lukis terbalik lah. Okay. Nah, this one. So for this polarity positive negative, so the switch is off, current can flow. For this one terbalik, consider is off, current cannot flow. Open circuit. This one short circuit. Okay. Applications of switching lah kalau kita nak guna as switch. Ini kita dah explain tadi on forward bias and reverse bias. For forward bias, VD mesti ada value, it is not equals to 0 because of the polarity for the ni lah, external voltage source tu. Okay. And for the reverse bias, VD is less than 0, ID equals to 0. Okay. First kena determine polarity external field tu dia pergi dekat diode tu macam mana. Tapi in circuit kita tak lukis pun macam ni, guna this one. In circuit kita guna this one. Tapi in your mind you mesti kena ingat, oh kalau yang positif maksudnya polarity dia dekat situ. Okay. This one is in series connection. So it can flow macam ni. Okay, silicon berapa? 0.7. So how to do the KVL? Negatif. Syat. Negatif E plus berapa? Sebab sini kan, plus 0.7 minus plus VR equals to 0. Please remember VR ni equals to IR. So boleh tak cari I? Sebab value of R ni normally dalam circuit mesti dia bagi kan. Kalau dia tak bagi value R, dia akan bagi VR. Contohnya lah. Okay. Alright. So this is simple circuit with the diode. So dia boleh we can measure the current with the diode kat sini. Kalau dia buat terbalik, negatif positif, so we can consider this one, the diode is off. So I equals to 0. Sebab dia open circuit. Dekat sini lah. Dekat, kalau saya letak at A and B. Okay, nampak tak polarity dia? Okay. Oh, ni yang tadi kan? Okay, dah. Ni pun sama je tadi. So we can replace macam ni. Tak nak replace lukis balik pun tak apa dia. As long as you tahu, kalau silicon it is 0.7. So kalau soalan tanya what is value of the VD, VD equals to 0.7 terus. Kalau ada dua, kat sini ada lagi satu, ni VD2 0.7. Kalau if it is silicon, it can be one silicon, one germanium. So yang bawah tu kalau germanium 0.3. Okay, so sama je in the circuit. Letaklah 10 pun, kan? As long as dia semua forward lah. Kalau satu reverse, terus off, terus open circuit. Okay. Yang ni dah explain dah tadi. Kan? So this one will be open circuit kan? So I equals to 0, open circuit. So kalau find value of I, terus you tak perlu kira-kira dah I equals to 0 ampere. Justify open circuit because the diode is in reverse bias. Pandai pun. Ni explanation dia. Ni lah. Okay, VD equals to E because this one is at same node. Same node, so kita kira as value of this one. Okay. Dia macam this one is sini, katakanlah sini adalah A, so A ni E. So VD kalau kat sini pun sama, VD dari atas ke bawah, E dari atas ke bawah juga. Okay, sebab open circuit kan, dia tak flow dah dekat sini, tak ada current. VR equals to, dia macam minus E plus VD plus VR equals to 0. But then this one is, kita tahu 0 because I is 0 kan. So VD equals to E kan. Sama je buat KVL juga. Tapi from your knowledge, since it is open circuit, I is equals to 0, VR get 0. Dia takkan jadi VR ada value sebab VR equals to I darab R kan. Kalau I tu 0, VR 0 lah. So from the KVL terus jadi VD equals to E. Okay. Ni apa? Ni apa pula ni? Sama dengan yang atas lah It just this one dia letakkan value. Okay. So ini 8. Sama je kalau kita buat KVR. So kita akan dapat ni open circuit I equals to 0. Sini tak ada I. Okay, VD equals to 8. Ni lah sama kita buat tadi kan. Sama tak? Saya tunjuk tadi. Minus E plus VD plus VR equals to 0. So since this one is 0, VD equals to E ataupun V lah. Sama je, E ataupun V. Okay. This one for the ni saya dah tunjuk dah tadi, load line analysis or the diode characteristic I versus V. IV characteristic, diode characteristic ataupun IV characteristic. Sama je, benda yang sama. Ada berapa tadi yang saya bagi tahu? Ideal. Lagi? Germanium, silicon and apalah lagi satu tu? Zener diode. Okay. Kat mana dia cut ni depends on silicon 0.7, germanium 0.3. Kalau Zener it can be both, tapi dia cater untuk reverse bias. This one is forward bias, this is reverse bias. Untuk ideal, dia kena macam ni je ideal. At V equals to 0, I ada value. Ni V equals to 0. Kat sini je dia akan on. I, V. Ideal diode. Consider this one is switching lah. Kan? Dia ada dua position dia. On, off. High, low je. Betul tak? Okay. Inilah. Kenapa saya cerita awal baru ada slide It is actually this one for this chapter 2 and chapter 3 saya selalu ajar online. Jadi kalau you guys tengok tu media ni cerita awal pasal slide baru datang. So benda ni lah tadi kan kita dah buat kan. Okay. Okay, this one is on the load line operating point. Operating point ni penting because bila kita nak buat sesuatu, kita kena tahu the optimal point. What is the optimal value yang kita nak tetapkan. Okay. This is for load line network. Yang ini, this is for the diode characteristic. This one, characteristic. Okay. IDQ, Q is the Q point ataupun the optimal point, the operating point lah. Normally when we want to set for a system, kita mesti tahu what is the optimal value so that dia akan jadi the most efficient system kan. Okay. So to find the load line, ini adalah from the equation of the circuit yang biasa. V equals to VD plus yang tadi kita buat kan. Tadi E equals to VD plus VR tu. So it is actually comes from there. Okay. When we set VD is equals to 0 ataupun in this one in reverse bias. VD is, when we set VD is equals to 0, ID is equals to V over R. Okay. And this one when we set to ID equals to 0, kita boleh dapat ID is equals to I. Kan dia series kan. Okay. So this one is 0, dia dapat VD equals to V. Tu yang kita dapat the load line tu. Mana dah? This one. At this point, yang ni is when VD equals to 0. Yang ini is when the ID is equals to 0. So bila kita masukkan the value tu yang dapat plot this one. Yang load line ni, this load line. Okay. This is the apa kita panggil, assumption kita lah, because on the axis, satu axis X, satu axis Y. Okay. Ni draw the load line yang tadi tu. Intersect between the load line and characteristic curve is the operating point. Characteristic curve yang ada 4 jenis tadi. This is the load line, depends on the circuit. So this will be the intersect, the operating point dia lah. Ideal diode is a simple switch. In forward bias, kita consider as a close. Kan tadi dah tengok. In open circuit, it is off. So kalau in forward bias, VD mesti ada value, either 0.7 ataupun 0.3. Kalau in open, ID must be 0. Sebab open circuit kan, there is no current flow. Okay. Ni tak ada apa. In real life no diode is ideal. That is why bila kita belajar, madam kata ada ideal diode. Bila you buat eksperimen, you nak measure mesti ada value, because dekat dalam transistor yang kecil tu kita main dengan elemen kan. When we inject impurity semua, it is very impossible untuk dapat the ideal cases. Dia mesti ada juga sikit yang flow, sebab ada diffusion current tadi tu, the one yang kita tak boleh nak measure kan. Dia by default, bila kita tak positif negatif, dia mesti auto ada. Kita tak boleh nak cater on that part. Tapi it is very small value. Okay, tetapi in some point dia akan kacau juga on the ideal condition tu. Okay, as long as the operations dia tak terganggu, still forward, kita nak forward still jadi forward bias. Tetapi dia akan ganggu kalau in ideal conditions lah, dia akan kacau sikit. Okay, alright. Ni this one is, kita nak habis kat mana ya? Example 1. Sebab this one je lah example 1 ni kita tengok. Okay, nanti kita tengok lagi on the, tapi ujung ni dah tak ada apa dah sebenarnya, circuit je. Okay. Alright, so this is for find the VDQ and IDQ. We set for VDQ and IDQ, kita set VD is equals to 0 and ID is equals to 0 kan. It is kalau kita nak buat based on the operating point. And then from here, this is ID equals to ID equals to IR. Sebab series kan? Okay, so IR equals to IDQ, VR equals to IDQ R equals to berapa? 10 minus VR kat sini. What is the value of VR? 10 tolak kan? Dia katakanlah ni 10 pergi ke diode, pergi ke resistor, ke ground. This is 10, this is 10, 0.7, this is VR. So 10 adalah dari atas ke bawah, VR dari sini. So VR is equals to 10 minus 0.7. So by default kita tahu kat sini VR is 9.3 lah. 9.3 ataupun equals to E minus VDQ. Okay, so VDQ is 0.7, somewhere dekat sini, sinilah. Ni. Okay, and at VD equals to 0, I equals to 10 over 0.5, dapat 20 kan? I equals to V over R. R dia berapa tadi? 0.5K. 10 over 0.5K. Tu yang dapat sini. Okay. At ID equals to 0, VD equals to V source kan? Sama dengan voltage source kan? Equals to 10. Tu yang dapat this one. At these two condition. Okay, so kita line kan, and this is the operating point dia, IDQ. VDQ tarik pergi bawah ni, dia almost lah 0.7, 0.78. Okay, depends on yang kita lukis. Okay, this is the approximate model. When we compare with the ideal, ideal adalah 0.7. Sebenarnya bila kita lukis kat sini, bila kita tarik, it is bukan 0.7 tapi approximate lah, almost, due to the ideal condition. Dia tak akan dapat 0.7. Okay, ni tak ada apa. Ni lah yang ideal diode saya kata tadi tu, this one. Dia macam ni. Okay, dekat this one dekat forward bias, ini for reverse bias. Yang ini tak ada apa, just sama dengan atas tadi, operating point. Okay, let's do this one. Ni apa? In general, a diode in on state is the current established by the applied, meaning that I flow in the series is IR equals to ID lah. Kalau in series, dia boleh jadi series, dia boleh jadi parallel juga. Okay, for silicon minimum 0.7, tapi kita set 0.7 lah. Tapi when we calculate Katakanlah kita buat KVL tiba-tiba dapat 0.8. So dia boleh jadi. By default, kalau tak bagi tahu the value, then we use 0.7. Same goes for the germanium. Okay. For this one, ni simple je ni. Okay. So since it is dia bagi tahu tak silicon. Okay, so silicon terus tulis 0.7. Normally kalau dia mention silicon terus tulis. Biasanya ada markah lah. Okay. And then buat KVL biasa. Dapatlah. Ni simple je kan? Sama macam tadi kan? So skip je lah. Okay, ini if we change the removing the diode, consider as a reverse condition lah. Maksudnya it is open circuit, so current cannot flow. I0, so voltage in here is equals to voltage minus VR. VR is 0, so dapat sama. Okay. Okay, so this one. Kita buat yang ni. Untuk A, untuk number 1. For number 1, both is silicon. Kalau both is silicon, VD1 equals to VD2 equals to 0.7. So for the KVL, minus 12 plus plus 0.7 plus 0.7 plus IR1 equals to 0. V out dekat sini Bila kita lukis, dia sebenarnya ini adalah V1, diode 1, diode 2, resistor, ground. D1, D2, this is R. So VR is at this point. Okay, ini adalah V1. Okay, this is V up. V1 dari atas sampai ke bawah. D1 sini je. D2 is here. VR is this one. Nampak tak? So D1 plus D2 plus VR ataupun plus VR equals to equals to V1. Ni kan semua V1. VD1 plus VD2 plus VR equals to V1. Ataupun minus V1, ni kan V1 kan, tambah VD1, VD2, ini adalah VR ataupun VR. VR is equals to VR. Ni sama je ni. Sebab dekat sini dia ambil daripada sini ke sini. Okay. So what are the value of I? Get me the value of I. I berapa? I berapa? Nak panggil nama lah. Nur Putri Zari Sofia, which one? Okay, you sekarang, this is your second time ambil. Okay. Alamak, siapa tak ada. Kenapa sebelum ni tak pernah datang? Baru register for this class. Okay. Sebelum ni masuk kelas mana? 3C. So why did you change to this class? Siapa 3C? Siapa? Everyone yang lain tolong kira what is the value untuk I for since for Zarif ni, this is your second time ambil. I hope that you still ingat lah. Macam mana nak kira KVL semua Tiga C 3C. Madam Hashimah, dia tak rasa, dia tak reply ke? Oh, tapi kelas tak pernah pergi dengan dia? Dua orang? Sebab kelas dia ada je ni 3C. Okay. Siapa lagi yang this is your second time ambil? Muksid pun tak ada ni. Muksid tak ada. Yang ada lagi seorang yang Khairul Nizam pun tak ada. Okay. For Putri Zaris, next class I want you duduk depan And setiap kali for yang second intake, second time ambil, third time ambil, setiap kali kelas kena duduk depan dan tak boleh absent. If you absent, kena bagi tahu saya lebih awal lah kenapa you sakit ke apa ke. Kalau tak datang 2 kali 3 kali berturut-turut, nanti I will do reporting tu. Dia ada borang dia sebenarnya kalau yang tak datang. I have to be strict untuk for those yang dah pernah ambil. Kita tak nak you repeat lagi. Okay. Ni bukan nak bias ke apa Okay. Alright. So what is the value? Sama ke dapat semua? 1.9 ampere. Okay. Alright. So actually for okay, tak apalah, nanti I bagi tahu once dah sudah. Okay, so that one. Untuk nombor 2? Nombor 2 dah ada yang buat tak? Berapa? Oh, milliampere. Okay, milliampere. Okay, so I equals to IR ataupun ID semua sama because it is same node, same circuit kan, series. Okay. Okay, for KVL untuk kita buat KVL dulu. KVL for number 2. Both is germanium. Germanium VD is equals to 0.3. Okay. So minus 12 plus berapa? 0.3 plus 0.3 plus IR1 equals to 0. Okay. Get me the value of I. Zari Sofia dah masuk dah WhatsApp group? Bila? Oh, okay. We have YouTube channel untuk for this class, daripada first class sampai today. So saya uploadkan semua dekat YouTube channel. Please study balik for each of the class. Satu class satu video. Tolong study balik based on the notes untuk revision lah. Yes, you are the second timer tapi revision kan? Okay. Alright. Nombor 2 dapat berapa? What are the value? 2.04 milliampere. Okay, very good. Number 3. Number 3 is 0.7. This one is 0.3 kan? Okay, KVL dia minus 12 plus 0.7 plus 0.3 plus IR1 equals to 0. Sebab tu pentingnya for you to determine dia punya silicon ataupun germanium. And also untuk determine polarity dia. Ni. Kalau tiba-tiba polarity dia terbalik, then terus I equals to 0. Okay. So for this one, what are the value? For number 3? Berapa? 96 milliampere. Okay, very good. Dah kemas beg dah. Sakit perut. Okay, kita tengok bawah ni ada apa lagi? This one pun sama macam tadi kan? Sama tak? Dia sebenarnya circuit boleh lukis macam ni Ataupun the circuit boleh lukis macam ni juga, like I tunjuk tadi. Okay, so this is 5.6 and V out dia dekat sini. Okay, okay, yang tadi kita nak lagi satu is V out kan. So V out dia berapa yang ni? Get me V out for each one. Sebab soalan dia sama dengan soalan ni, next one ni. Berapa V out dia? V out ni lah IR1 tu lah. Darab dengan the resistor value. Berapa? Must remember dia ada mili, yang ni ada kilo. Berapa? Kat sini, V out dekat sini. Berapa? 10 point? Okay, second one?
11.4.
11.4 yang second. Yang ketiga?
11.
Simple je kan? It is simple series circuit. So kalau dapat KVL pun simple je. Tapi in order to solve, kita kena determine polarity dia dulu. Sebab nak tahu dia on ke off, kan? And then kita kena tengok silicon ke germanium, baru kita boleh buat KVL dia. Okay, very good. This one, for this saya just nak tunjuk V out is dekat sini, sama macam tadi. It is the current yang flow darab dengan the resistor dia tu. Okay, so we just keep this one. Yang ni pun sama juga kan? Okay, for this one, dia punya circuit is, dia ada resistor, we have the diode, we have the another resistor, we have voltage, baru pergi ke ground. Okay, so yang ini adalah 10. Tengok saya lukis ni. This is 4.7K. This is silicon equals to 0.7. This is 2.2K. Yang ini adalah 5. Kenapa saya lukis macam tu 5 tu? Nampak tak beza dia? Kenapa saya lukis macam tu? Sebab dia cakap sini negative 5. So dia akan jumpa negatif dulu. Ada kelas ke? Sekejap, lepas ni ada apa lagi? Alah, panjang lagi. Okay, yang ni sekejap yang ni, yang negative 5 ni, nanti kita sambung. Okay, so KVL dia from here minus 10 plus 4.7K I plus 0.7 plus 2.2K I minus 5 equals 0. Sebab dia ada kat sini, dia berbeza dengan yang tadi. And then the V2 is dekat sini sahaja, which is dekat point ni until here. Okay, kalau V2 dekat situ sampai sini je, dia tak sampai ground tu. Nampak tak dia buat sampai sini ni? Okay, so for V2 dekat ni je, at 2.2 resistor. So once dah dapat, masukkan dekat sini. Okay, boleh. Cuba buat this one, nanti next class kita sambung. Sebab ada kelas lain dah. Okay, for the explanations yang mana ayat-ayat panjang, kadang-kadang saya explain dulu baru ada dalam slide kan. So please tengok balik. Harap-harap sama lah explanation saya dengan dalam slide tu kan.